Google's Pathways language model and chain of thought. Pathways language model, or PaLM, the largest model of early 2022, outperforms average human on grade school logic and math by simulating reasoning steps. Okay, hello. So this is a new video. Today I read super long paper, Google Pathways. Go into lots of details. And this is a sort of short preparation on a little bit longer talk that I will have at Glame. I will link to a meetup tomorrow evening where you can as well ask questions. You can join that event if you need, if you like. And yeah, I write this blog where you can subscribe. I'm preparing OpenAI DALL-E as well. And you can subscribe to these posts by mail, subscribing over here. You can subscribe on Twitter, YouTube, LinkedIn, Facebook, RSS. You can donate here. And yeah, so you can as well like and ask me questions. So let's go on Google Pathways language model. One quick note, lots of things I'm learning on the go while I'm using machine learning models. I have some experience. If you see any mistakes, let me know. I'm happy to correct potential issues. Okay, so let's go. So Google Pathways is the biggest dense transformer model, 540 billion, likely most expensive early 2022. It's highly efficient training using 6,000 chips TPU version 4 across 2 clusters pods. Improvements from scaling, it shows that improvements from scaling continue in language understanding when using few shot approach. And it also shows that there's some things are just showing this. On some tasks, the language models are showing disproportionate gains from certain scales. For example, in reasonings, there are tasks where there are rapid improvements after achieving certain model scale, speculating that these are about model achieving certain level of abstraction. As well, this model shows breakthrough performance, outperforming average human on grade school logic and math, specifically big benchmark. Not all tasks, this is not uniform. On some tasks, average humans still win. It outperforms specialized and fine-tuned models on multi-step reasoning, and the paper studies chain of thought prompting, which sort of simulates inner monologue or inferent steps of reasoning. Model pre-training task, just to go a little bit deeper. Here, this is a autoregressive language model like GPT-3. So it gets text and predicts the next word or token. And so it is a transformer, it is attention model, but it looks only into the past. Okay, how big is the PaLM language model? Well, it is a transformer architecture similar to GPT-3, but it has 3 times the parameters. It is twice smaller than switch transformer, but the switch transformer is different approach. It's a sparsely executed transformer, and PaLM is shows still a better result. For comparison, PaLM has 540 billion parameters. Human brain has 100 trillion connections between neurons. It is likely the most expensive model to date. We don't know exactly the cost, but it's probably twice the cost of GPT-3, which is interesting because it's compared to the number of flops, it's actually only twice more expensive, I think. While it has 5 times the computation, it's only twice the cost. So the costs are also going down. It's twice the computing cost of Megatron Turing LNG. just want to note that the huge models are fascinating, but I think they are not very economical at this moment. GPT-3, you can buy it, it's relatively cheap, but I don't think OpenAI is actually making huge money on it. If we look at this graph down here, we can see comparison of the number of computational costs that were used to train large AI models. The palm is up here, right? It has twice the computational cost of megatron Turing. This is linear scale, and GPT-3 is down here. It used much less. So why it's more than megatron Turing, which has 530 billion parameters, while Palm has it's only a little bit bigger than megatron Turing? Well, it's because it probably has trained longer or has bigger training data. Uh, yeah, actually, I should look into this, which I don't have this prepared now. So the comparison between zero-shot, few-shot prompting versus fine-tuning. So prompting, what is prompting? So actually, this is natural language. These are natural language models, and these are autoregressive. So we provide the text on input, and it generates how the text continues. And because this setup is super general, the output can be effectively unlimited length or unspecified length. We can, as part of the input, provide different tasks and instruct the model to do something for us. How would we do this? This is called prompting. So we can, for example, in case of zero shot, we only describe the task but give no demonstrations. And we expect then upon the question to receive the correct answer. For example, we can ask how to translate to cheese by saying to the model, translate English to French. Cheese equals what? And in case of few-shot learning, we describe the task and provide some random demonstrations. So translate English to French and provide one example. Sea otter is l'outre de mer, for example. And then we ask, and cheese, how do you translate cheese, right? You say cheese equals what? Okay, and fine tuning, that's something completely different, because in this, we were just doing prediction. We just gave something to the input to the model and expected the output that would answer our question. In case of a fine tuning, we are actually editing, updating the model. We are doing gradient updates to the model, changing the model parameters. So fine tuning is different. Usually fine tuning fine tuning is usually much smaller than pre-training, so the training is much bigger undertaking. It has much more data involved, but this is still significantly different from the zero shot, one shot when we do nothing. Okay, so but the fine-tuning instead is something that you can do some additional training at the end of the very general model. So the zero shot, one shot is this big also difference that when we use zero shot, one shot, usually we have some super general model that can do many things. But we just ask it to do, we can ask it to do many general things. Okay, so what breakthrough capabilities the Palm actually has? So on Big Bench, which is Google's benchmark, it has 150 tasks. Each task contains samples, so it's more than 150 samples. It's a little bit, it might be confused. It's many samples. And the samples are reasoning, math, question answering, translation, programming, are relatively difficult for humans as well. And only 58 tasks are available on other models for comparison. Palm is state of the art on many of the tasks. It outperforms average human, and state of the art, which are GPT-3 Go for chinchilla. At the same time, on some tasks, it still underperforms human. It's a bit funny note because there is a huge risk of contaminating your training data because lots of the training data is scanned from the internet, and if accidentally someone includes the big bench, the model could be then trained on these tasks, and then it would be easy to achieve good performance. So that's what we need to be careful about, and they prevent it by adding additional ID into the text and then scanning the data set for the ID. What's interesting about the results on Big Bench is that certain capabilities emerge at certain scale. So, and we can observe it by the results by being non-log linear. So for example, here we are 10xing the model size, and the improvement is linear. While on English proverbs, once we reach a certain scale, there is a big jump in performance. Yeah, this is non-linear. This is also non-linear logical sequence. Okay, so it was interesting. Okay, let's go. Chain of thought prompting. Chain of thought prompting is again approach where we can modify what we give to the model on the input. We can modify the prompt. We can modify the demonstrations we give to the model. What we do is we insert reasoning steps between each demonstrations and the correct answer in the few-shot learning, and then the model tries to simulate this inference thinking, this inner monologue. This is very useful in multi-step arithmetic, where you need to convert some natural language questions to equations. In common sense logical reasoning, we have some chaining logical inferences based on strong empirical knowledge, and useful for interpretation as well, because if we see what the model thinks, we can then see if it's for the right reasons. Well, at the same time, let's look at the improvements in the results thanks to chain of thought prompting. So on the reasoning dataset, for example, GSM 8K, there is improvement over the GPT-3 fine-tuning with calculator and verifier. So Palm outperforms. It at the same time, it's obviously bigger, but what's interesting about this result is that inference chains, chain of thought prompting improves drastically the results. So if we look at this graph, so the best results from previous work is here. Direct prompting is this dashed line, and we can see on some of the tasks like GSM 8K, the improvement is really dramatic from 20% to 60%. And yeah, they outperform all previous works on these tasks, not only GPT-3. Yes, so let's go. What's also interesting about the chain of thought prompting is that you can ask, okay, if this chain of thought prompting is helping, if there are some reasons, some inference in these reasons the model comes up, are those right reasons for the right answers? And the interpretability also may be desired output of the model. So in their setup, in this comparison that follows, they use two-shot prompting with greedy coding, and I tried to reproduce the exact same approach using GPT-3 for $0.1, relatively cheap experiment. Just wanted to give you some additional insight, some additional comparison directly with the GPT-3. And of course I set the zero temperature because I wanted also deterministic decoding. Okay, so the input to the model, apart from the, you can find the exact input in its entirety in the appendix of this post, but so let's look at this. Input is, then the question basically is, Jennifer looks out of her window and sees a really cool cloud below her. She unbuckles her seatbelt and heads to the bathroom. Is Jennifer probably traveling more than 300 miles per hour relative to Earth? So Palm says 300 miles per hour is about 480 kilometers per hour. This is about the speed of a commercial airplane. Clouds are usually below airplanes, so Jennifer is probably on an airplane. The answer is yes. So one minor issue is here that the average plane speed is about 400 to 600. 500 to 600. And so the first part is not entirely correct, but otherwise it's very cohesive explanation. It's very much makes sense. It's very nice. Let's look at the GPT-3 sets. So GPT-3 sets no, because an M-brain typically travels around 500 to 600 miles per hour, which is true, but it's not true that this is no, because we are not asking about if the 300 miles per hour is the exact value. We are asking if Jennifer is traveling more than 300 miles per hour relative to Earth. And as well, GPT-3 says, and the bathroom is usually located at the back of the plane. So this part of the sentence is irrelevant. So here we can see that the GPT-3 produces indeed worse results here. Okay, let's go. Palm on code tasks. So this is very interesting. Even though they haven't trained specifically to produce code, they actually achieved similar results to OpenAI Codex 12 billion, which is much smaller model. But as well, they used the Palm used much less training data. After fine-tuning, they can outperform the OpenAI's best model, DaVinci Codex. But yeah, it's still a smaller model, the DaVinci Codex. But it's good to see that they can get good results. There are many other tasks. In general, if you showed is not really competitive with the fine-tuned models, but FewShot can outperform all other. It's generally state of art compared to the other FewShots, but the fine-tuned models are better. Especially on the summarization, the fine-tuned results were much better than FewShot. What was interesting that for translation from German to English, Romania to English, the FewShot was actually better than supervised baselines. Super interesting. Okay, architecture. So it's a code-only transformer, so you antenna only to the past, like GPT-3. It has a modified feed-forward layer. So instead of a ReLU with this linear output de facto we use swish glue, and we gain about 1% of accuracy in compute equivalent setup. So why is this better? Well, as I mentioned, we use a GLU, gated linear unit, which basically is sigmoid controlled output. So somehow this is more general, and thanks to being more general, it works. Seems to work better. By the way, this switch activation is just similar to ReLU. It just is slightly different. And yeah, so here's how the gating exactly works. Also, they use parallel attention with feed forward layer, which they were inspired from GPT-J. So instead of sequential, these two layers are additive, so you can get speed up, parallelization. Nice. Multi-query attention. So here, their attention uses same key and value projections for all heads, but different query projections. And this speeds up autoregressive decoding. Normally, we would have for all key, value, and query different projections. Here we share keys and values. Rope embeddings. So embeddings are there to encode relative positions between the embeddings, between the tokens, between the word vectors, right? And we can actually achieve it very simply by just using rotational matrix. And the rotational matrix makes sure that when you are doing dot product, we will be dealing with the relative positions. But how exactly? Well, in this case, they just use rotational matrix along the diagonal between the nearby two dimensions and improve performance along sequences. Okay, training dataset, 700 billion tokens of high quality text, which is not the biggest. For example, massive text is 5 trillion tokens, GPT-3 used 300 billion tokens, Turing LNG 339 billion tokens. And yeah, it's private, non-reproducible, 50% social media, 27% web pages. Basically, it's mostly from the web. Contains art, mostly arts, entertainment, games, some reference, computer electronics. Palm training requirements. So it's a huge model, 17 terabyte of RAM required, 2.5 yottaflops. That means 10 to the 24 flops needed for training. So because it's such a huge model, we cannot use a single machine, of course. So we use many machines, and the mind of Palm is then shattered across the many chips. And each of those, but thanks to that, each of those parts, each of that hardware is replaceable, it's coolable, and it's cheap. And so they use in Google two TPU version pod clusters. They are connected via data center network. Each pod can calculate 1 exaflop, which is 768 hosts, 3000 TPU versions for chips in each pod. But how do we split the work and communicate? Okay, how do we do that? So actually, training large models. This is a big problem. It deals with parallel computing, which trade-offs compute, memory, and communication throughput. The most simplest approach is just use data parallelisms, where we just split the batches between the workers. We calculate the gradients, we exchange the gradients, and update the models. Then we can do as well as the tensor model parallelisms. For example, we can split the transform along the calculation tree, right? And to do that, data cyclic to do that, we can, for example, split transform block into attention heads and feed forward layers in our case of Palm language model. Then there's another approach which was used in Megatron Turing, which is pipeline mechanism. We also can split the model along its computational graph, data acyclic graph DAG, into stages. Each computation can be split into stages, and in this case it would be layers. Then the stages exchange, they calculate forward and backward and exchange information between the layers. The issue here is that it creates these bubbles, idled computers that wait are not utilized, but they are stock blocked. So instead, in Palm language model, we use pipeline free parallelism or 2D parallelism. It so means that we use data parallel and tensor parallel. So each cluster has a full model copy. Model is partitioned into 12 parts. Data is partitioned into 256 parts. 768 hosts are connected to 3000 chips, which are connected in some local quick communication buses. And after each batch, the clusters exchange the updates and get to those identical models. So we have two clusters. Then after each, so these are data parallel. After each update, they exchange, the hosts talk to each other and exchange 1.3 gigabyte of data and get to the same state. Okay, training efficiency. So in the paper they introduce observed throughput relative to theoretical maximum throughput of the system as a good way to measure sort of the price for parallelization or efficiency of parallelization. And the Palm language model achieves 50%. Yes, and so this would be end. You can find the prompts here in the appendix. You can try it on GPT-3 for yourself. Yeah, you can play with the jokes as well. Yeah, and yeah, subscribe. You can let others know, and if you like it, you can ask me a question. And yeah, I'd like to see you in the future. See you. Bye.